Okay, thank you. So I will present the paper Unchain Your Blockchain. This is, I'm Yaron, and this is a joint work with Parnidas and Divesh Srivastava. And as said, we are from AT&T Labs Research. So you all know that blockchain is gaining a lot of interest and popularity. That's why we are all here. Many applications started with cryptocurrencies, but now spreading to many other domains are being suggested, and some of them would be discussed here. However, there are still three limitations that pose a challenge to the research community. One of them is lack of scalability. So the transaction rate in leading blockchains is still very low, a few transactions per second. In particular, Bitcoin, Ethereum, you cannot scale to the level of thousands of transactions per second, which you expect in a commercial system that, for example, process credit card transactions and things like that. There were several suggestions like electing a leader that would create several blocks rather than a single block, or creating a DAG rather than a tree when expanding the chain. However, all these increase the transaction rate. They don't scale up as the need grows. Okay, so there's still a need to suggest a way to scale up. And right now, if you add more nodes to existing blockchains, you increase the trust. You don't scale. The other problem is of insufficient security, in particular in cryptocurrencies. If a key is stolen, it's like stolen money, right? And adding more limitations and the way you would use cryptocurrencies could help increase the security. And the limitation that received the most significant attention is the waste of energy. Bitcoin is consuming a lot of energy, much more than many countries in the world, right? This is a real problem. It limits the ability to actually have much more chains of that nature. Our suggested solution is it comprises three parts. One is an hierarchical partitioning of the blockchain. We suggest geofencing to restrict transactions and add security, and proof of location as an alternative to proof of work in order to save energy. Before I get into those solutions, as a background, I need to introduce the concept of location certificate. So suppose we have a user with a private key K, Alice, and she wants to produce a location certificate. She would need some localized corroborator, which is a device in a known location and that can only be accessed directly, either physically through some wire, or it could be a cellular antenna, a Wi-Fi access point, or something that can only be accessed directly from a short range. And this is something that is integrated in the network. Once you have that, we can measure the round trip between Alice and that corroborator, right? Direct access is, according to our measurements, is usually a few milliseconds versus indirect access if you want, for example, to tunnel the key to a remote user, that would take you dozens of milliseconds or much more, right? So you can clearly distinguish between direct access and indirect access, and once you're doing that, you can issue a certificate that attests that someone with the key K was at the location of the corroborator or really near the corroborator at the time of the certificate. Okay? It works as follows. Initially, the public key of the user is sent. The time is recorded by the corroborator. The corroborator creates a session ID, some arbitrary value. The user signs that key using the private key and sends the signed value to the corroborator. The corroborator has now the time of arrival. It can compute the difference to find the time of the round trip and verify the signature. If all is well, then a signed certificate is given to the user. Okay, so now we have this certificate. You need to notice that, one, the certificate can be created at different granularity. It can be created to an exact location, to a city, to a county, to a country, etc. We can also restrict wallets to specific locations so that we now associate wallets, or if you want addresses in the terminology of Bitcoin, to a specific location so that we could only use that wallet or that address in that particular location. And in the following examples, I would mainly focus on cryptocurrencies because it would help explaining, but our results also apply to other domains. Just try to use the imagination and think of different types of transactions. However, in this case, we would note by X, denote by X, right arrow Y, a transfer of money from some address X to an address Y. So consider a large area. We assume that there's corroborator spread all over the area. Their spread can be such that it doesn't have to be homogeneous. The number doesn't have to be limited. And there could be, if you take an area which is large enough, there could be many corroborators by different companies, by different providers. Again, they could be designated machines in data centers, they could be Wi-Fi access points, they could be cellular antennas, etc. So the question is now how to use that to solve the problems that we just mentioned. The first thing I would like to talk about is the hierarchical partitioning of the blockchain, where it can be different. There are different hierarchies that can be used, but in this talk I would, of course, focus on the geographical one that uses the location certificates we mentioned. This is in particular important when you have transactions or usages that have some geographical facet or geographical connection. For example, when you transfer cash between people, they are in the same place. They really, you know where it happens. Or real estate, when you record real estate transactions, location is a very important factor in that. What we have is a partitioning, a hierarchical partitioning of our geographical area. For example, you can start with all of the USA, then you have the different states, different counties, different cities and towns, etc. And we associate a different blockchain to each one of the nodes. Okay, each blockchain here is independent. Their consensus is independent. They work independently. They don't even need to be of the same type. They can be different implementations of blockchains. Okay? Now each address or wallet, whatever you prefer, address is a little bit ambiguous, right? When I talk about address, I talk about, again, address in the sense of Bitcoin, not address in the geographical sense. So each address is associated with exactly one blockchain. And now we have a literal transfer is the usual transfer. You have two addresses in a single blockchain, and they transfer money from one address to the other. Okay, that's not different from what we currently have. But there are also ascending transfers and descending transfers where, for example, if you have an address X at a state and an address Y at a country, at a county in that state, then a transfer from X to Y is recorded at the blockchain of the state. Now, after doing that, because Y is associated with the node of the county, you can only record the next transaction, the one that spans X to Y. You can only record that in the county. So this, for example, prevents double spending, because if, for example, you want to spend the transaction X to Y somewhere else, it needs to be recorded only in the blockchain where Y is associated to, the one Y is associated to. So you can't record their two transactions. That is what the blockchain would prevent. Now, if you, again, want to transfer money within a single node, for example, two users want to exchange money in Newark, that's fine. Just record that in the Newark blockchain. But what if a user in Newark wants to transfer money to a user in Jersey City? So here we need to have a series of transactions. First, the user in Newark sends the money or applies a transaction that transfers the money to an address in the Essex County where Newark resides. Then a transfer to New Jersey. In New Jersey, in the blockchain of New Jersey, they can transfer between them, and then the second user can start lowering that, transferring the money to Hudson, and then to an address in Jersey City. Okay? What we get here is some trade-off. Users can work at a high level. They don't need to work at the blockchains at the lower level. This would give them more privacy, but they would need to compete with transactions